Okay, let's get started. Let's talk a little bit about the deliverables. Everyone submit deliverable 7 last night, more or less? Okay. For those that have, you're over the hump. 8, 9, and 10 are much less onerous than 6 or 7. Who has a system that can recognize all 10 numbers pretty well? Okay. That's good. Okay, so some of you are still working on deliverable 6 and struggling to get your system to recognize all 10 digits. As I mentioned on Tuesday, remember that we have a large class and there's a lot of redundancy in the data set. So if you find that a pair of numbers isn't working well, go back, find another student who recorded the same numbers and swap their data in. Rinse and repeat until you've got something that can do well on all 10 digits. Margaret. Yep. Yep. If you did it like this rather than like this. Absolutely, right? So there is a lot of heterogeneity in the data set. Remember our discussion the first few weeks about packed analysis? We have a lot of different people in this class, and people might have recorded things differently. Some of you might have recorded 0 like this. Some of you might have recorded it like this. Some of you might have recorded it like this. And if you read in someone else's 0 and you're signing like this, it may or may not recognize it, right? So there's a lot of differences in the data set, and that is what deliverable 6 is all about, is getting you to figure out how to deal with all this disparate data. We are not expecting that you read in every single student's data set and use that in your system. You're looking to get a set, to find enough data to cover all 10 digits so that you are able to sign all 10 and your system recognizes it. And then you take the way that you choose to sign all 10 and create visualizations to teach your users to sign in the way that you sign that enables your KNN algorithm to recognize those 10 digits. That's how 6 and 7 work together. Yeah.
If we have like one digit that isn't doing very well, would you recommend that we change the data that we're using or just add another?
The easiest thing is change it. So if it's a single digit, just remove that training and test set and read it in from someone else's. Yeah, exactly. Feel free to mix and match.
When we took the data, is like the training and testing like the copies from the same user?
Say that again. I don't quite understand the question.
When we downloaded the data,
yes.
It's like copies of each other. So like train 1, copy 1, or copy 2. So is the training and testing the same one, or did we?
The training and test that's in the aggregate data set is exactly the same way in which you recorded your training and testing set. Right? The first 1,000 frames and then the second 1,000 frames.
Sorry, I mean, so like if the student submitted like test 2 and train 2,
yes.
Like will they be in the same order, or is it just randomized like different data sets?
I guess I'm still having a hard time understanding the question.
Is that weird?
What he's saying is that like all of the training and testing data is saved with like the same name, and then there's like a copy number next to it because they all have the same name.
Yes.
So it's like copy 1, copy 2, copy 3. So he's asking if like copy 2 lines up, copy 2 of test lines up with copy 2 of training, I think, right?
Yeah, more or less.
They're not tagged with the name.
They're not tagged with the student name. That's right. So copy 1, copy 2. That's right. Yes. So I'm sorry. Yes, it should line up. So copy 2 is from the same student. That's right. That's right. Okay. Sorry, I didn't misunderstood because the TA put together the aggregate data set. Yes. Margaret. That's all right. No problem. It may or may not matter whether you line it up. In theory, it shouldn't really matter. One person's train should be relatively close to another person's test, but not necessarily, right? Okay. Yes?
Are you okay with us putting digits in our program? Because those aren't necessarily universal, but they're more universal than the English language.
Yes, that's right. So exactly. So we're assuming that your user does not speak English, but they recognize the digits
Okay.
0 through 9. That's right. So you can actually draw the actual digit. So when you ask the user to sign 0, you can write 0, 1, 2, or so on. That's fine. Yes?
Do we show them also the sign?
Aha. So do you show them also the sign? That's going to come up in 9 and 10. So deliverables 9 and 10 are going to be focused on how do you actually go about teaching the users to do so, to actually sign correctly, right? We haven't got to the teaching part yet. At the end of deliverable 7, you should at least have your user holding their hand centered over the device. So we'll come back to that in 9 and 10. All right. Any other questions about the deliverables? Okay, I mentioned this before. I asked the TA to go back through the data sets, and some people save things in slightly different format. I'll check with the TA today whether he's done so, and if he has, you can download the data set again, and hopefully all of the files in there are in exactly the same format. Okay, so again, some of you might be having a hard time getting your KNN algorithm to recognize certain digits because some people might sign like this, some people might sign like that. What other differences might be making things difficult on your KNN algorithm? Aside from the orientation of the hand.
Hand size.
Hand size, yep, that might matter.
I know some of the data is like lefty versus righty.
How many lefties in the class? Are none here today?
Yeah.
1. Okay, there we go. Thank you. Thank you. All right. So some people might have signed like this, and some people might have signed like that. For most of the righties in this class, you're probably not going to be able to recognize a lefty data set. That being said, you could add some code to your system to make it robust regardless of hand, regardless of orientation, regardless of left and right. What code might you put in so that your KNN algorithm can recognize lefty data even if the majority of the data is righty data?
You could reverse the hand, well, like the not dimensions, but the points of the hand, you could just reverse those.
Exactly, right? So you can take a lefty hand and turn it into a righty hand by reversing the hand. And remember that the hand data is being stored in this, originally in this 3-dimensional matrix, which has the x, y, and z coordinates of all the endpoints of the bones in your hand. So how specifically would you turn a lefty frame of data into a righty frame of data? Could take a lefty data and turn it into this. That's not what you want, right? You could take a lefty hand like this and turn it into this, which is also not what you want. You want to turn this into this.
Can you just reverse the order of fingers?
Not quite. It's not going to quite work, right? That one I can't demonstrate for you. Right? If you think about it, it's not going to. That's also not going to work.
Could you reflect it?
You can you reflect it about which axis? You reflect it about the x-axis, right? So think about all the x, y, and z coordinates in the bones of my hand right now. And then if we want to flip it about the x-axis, we'll get this, right? So take all of the x values in a frame of data and negate them, right? That'll reflect about the x-axis. So you can turn lefty data into righty data and vice versa by reflecting about the x-axis, by negating all of the x coordinates in the frame. Yes?
How to tell if it's like lefty data? Would you just check to see like if the thumb is like to whatever side of the fingers, or?
That's true. That's one way you could do it, right? So there's another way you could do it.
Doesn't Leap have like a built-in recognition of like lefty versus righty?
I think it probably does. There's probably a flag in there somewhere. The other thing you could do is take every single frame in your training set and double the size of that training set. For every single gesture, create the mirror image, right? So you double the amount of data, so it's in effect that all of you signed with the left and with the right. So there's some artificial things you can do that don't require doing complex recognition. Okay, so dealing with size is a little bit more tricky. You'd have to try and normalize the size of all the hands in the data set. That one's a little bit more tricky. And different orientations is even more tricky. That's why I had you try and do this manually. So better to just try and actually generate sign data at different orientations rather than sign at a given orientation and then artificially try and rotate frames of data. Yes? Sure.
When you are making a sign, does it matter if the image on the screen is not like, sometimes you'll do like this and it will look like, this or something. So does it matter, does it matter what your hand actually is, or does it matter what's shown on the screen?
Okay, so does it matter what you're actually signing and what's shown on the screen?
Right.
The answer is yes, it does matter because Leap Motion is telling you this is what I see, right? So this is going to be important, right? When you try and teach your users, remember your users are going to start to build up a mental model of what your system is doing. They know that it's trying to teach them sign language. You show them a picture of 0, they do 0, and the system says wrong, right? You've broken most people would predict that if they see a picture of this and they sign this over the device, the user, is doing everything correct, but the system is telling them they're incorrect, right? So you've broken the expectation of the users, which is a big no-no in HCI design, right? So we can't guarantee that your KNN learner is going to recognize the sign all the time. So how can we provide some additional feedback to the users to help them over the gulf of execution or evaluation, right? This is, the user did something and they didn't get back the result they expected. How can we help them figure out what's gone wrong or what they should do next to fix the problem, right? One thing is the wireframe. So the wireframe is the system telling the user, this is what I think your hand is doing, right? So when you get to 9 and 10, you're going to be adding additional visualizations to help the user learn sign language, but also to learn your system. How is it teaching you sign language? When your system makes a mistake, when the KNN algorithm makes a mistake, which it will, the user has to be able to correct things, right? We're assuming you're not there, so you need to provide something, and the wireframe is an important part of that, right? So you might show something on the wireframe and then give some instruction, some visual instruction to the user that if they do this and they see this, they should do this, or do this and then do this, or do this and then do this. Whatever it is, you need to provide a cue back to the user about how to fix the problem. Okay. Other questions? Yes?
Also, to kind of circle back,
Sure.
in Deliverable 7, we are showing the sign, we are pretty much teaching the user, we are showing signs that they need to do.
Correct.
Right?
That's
Okay.
right. That's the idea. Okay. So while we're on the topic of, again, showing images to the user, as I mentioned last time, Matplotlib wasn't really set up to serve as a real-time GUI. You can get it to do it. It's not ideal. It's up to you whether you want to switch to Pygame or not. If you stick with Matplotlib, the easiest thing to do is to break your figure down into multiple subplots, and then you can write or draw different things to the different plots. So in Deliverable 7, I showed you a picture of creating a 3D plot in one subpanel and a 2D plot in another subpanel. You can continue on with this, and at this point it's up to you how you want to do it. Some students in the past have made a 2x2 grid, so they had 1, 2, 3, 4 subplots. They would show, for example, the wireframe in one. They would use the upper right subplot to show images, sort of telling the user what to do. They would use this one down here to tell the user what particular digit they're supposed to be showing. And they would use this plot to say, yes, you're signing it correctly, or no, you're not. That's one way to do things. Lots of other ways to do it. What I would suggest, I would suggest avoiding trying to put a wireframe and an image in the same subplot. That usually doesn't work too well. So you want to sort of specialize each subplot to just one kind of visualization. Okay. And again, these additional elements will come up in Deliverables 9 and 10. All good? Okay. So that's 6 and 7. Let's talk about Deliverable 8. Hopefully this will be a little bit of a breather for most of you. This one is pretty short. What do we have? 4 pages, 14 steps, not too onerous. We're going to be adding some additional state to your program. So you have some state to your program now, which is whenever your code is running, is there a hand over the device? If there is it centered, and so on, right? We're adding internal state. But the moment you kill your program, that state disappears. In order to create your educational software, you're going to have to add some state to your program that's persistent. That state exists from one session to the next. Because, for example, you might have multiple users using your device or using your system. They log in, they practice sign language for a little while, they shut it down, they come back the next day, and they start up. They don't want to start from scratch. They want to start from where they left off. So in order to add that persistent state, in this week, you're going to be adding a database to your system. This is not a database class. We only have 1 week to add a database. So we're going to add the cheapest possible database you can add in Python, which is to simulate a database as a dictionary of dictionaries. How many people have worked with dictionaries of dictionaries? Some, but not all. Okay, so here's the idea. At the beginning of deliverable 8, at the top there, you're going to be creating a single variable called database. And as you can see, you're going to start by creating an empty dictionary. And inside that, and then once you create that empty database, you're going to dump it to a file using pickle. And then when you start up your program again, you're now going to load in the database from a file, which at step 3 is going to be nothing more than an empty dictionary. There's nothing in your database yet. Okay. When somebody logs in, you're going to ask them to type in their name, and when they do, you're going to add a new entry to a database. And in a Python, you're going to add a new entry to your dictionary. In a Python dictionary, you have a whole bunch of entries, and each entry is made up of a key and a value. The key is going to be the user's name. So I'm going to add an entry now to my dictionary, and that key is going to be a string, which is my name, and the value associated with that key at the moment is another empty dictionary. So now we have a dictionary with a dictionary inside it. If somebody else logs in to the system, we add a new entry to the database for that user, and the top level of the database is now going to be a number of entries which contains all information about that particular user. So far, so good? Okay. And at this point, let's see, let's keep going here. So we can associate lots of different information. So for example, how many times has Josh logged in? So we create a new element inside of this empty dictionary. And this element has this key, and it has as a value an integer. So remember that Python dictionaries can have any kind of data structure, for more or less any data structure for a key. In this case, our keys are strings. And we can associate with that key any sort of value we want. In one case, that value is a dictionary. For this particular element here, the key is a string, and the value is an integer, right? So again, not the most elegant way to create a database, but it should be good enough for our purposes. Okay, so Josh has logged in 3 times. And within the Josh element here, we might want to create a new element which is made up of a key of integers, such as 0 through 9. And the value over here is going to be a dictionary. And this dictionary is going to contain all the information about what I did when I was challenged to sign the digit 0. Right? So perhaps how many times was I shown the digit 0 and asked to sign that digit? Same thing for number number 9 down here. One of the nice things about using integers for the keys at this point is we could create a for loop and we could iterate through all of these digits. And we could do something like in deliverable 9 and 10, when Josh logs in, we could ask the question, which of the 10 digits has Josh been shown the least number of times? Pick that digit and show it to Josh. So somewhere in these dictionaries, you would include yet another dictionary, which is number of attempts, number of signs correct, number of signs incorrect, and so on. So in deliverable 8, we're sort of showing you how to create the top level structure for this dictionary. Towards the end of deliverable 8, and then throughout 9, 10, and the final project, it's up to you to structure the dictionary however you want. We don't care. Whatever information you want to track about the user, you figure out what that information is and how to encode it in this database. Sound good? Pretty straightforward? Okay. Okay, so let's get back to lecture material. We are working our way through this theme on looking outward. And as I mentioned last time, our society is in the process of sort of stitching computation and internet-enabled devices into the real world. In the old days, we had desktops and a few laptops, and they kind of talk to each other, but they were sort of separate from the real world, right? Now, as we start to stitch more and more computation and devices into the world, there are more and more of them. They talk to each other in more and different ways. And as we'll see when we get to lecture 16 today, they're also kind of disappearing into the fabric of the world. How many cell phones are in this room right now? You can't see them, you don't know, right? But probably one per person, right? And your phone may be on and it may be set to vibrate. So throughout this lecture, it may actually be providing you with information, but thanks to all of you, I haven't heard any of your cell phones yet, right? So you are communicating with your devices are communicating with each other, but it is somehow sort of disappearing into the fabric of our world. It's not that obvious anymore. That's important. We'll talk about that in lecture 16. Last time in lecture 14, we were thinking about broadening this single human, single computer interaction to a single computer, maybe multiple computers that are communicating with a large number of people. So last time we looked at 3 or 4 applications where the problem that we wanted to solve was impossible for one person to solve, impossible for one computer to solve, and also impossible for a group of people alone to solve, and a group of machines together to solve. So we looked at interesting ways of stitching together many different people and many different machines so that that hybrid team can hopefully solve the problem that would be impossible without that particular kind of team. So we were broadening or looking outwards in terms of sort of socializing our HCI, right? How do we get lots of people to work together with each other and also with machines to solve a problem that would be beyond a smaller group? Lecture 15, which we'll start in a moment here, we are also going to broaden our consideration of human-computer interaction, but we're going to broaden it not across lots of different people, but across lots of different sensor modalities, or our senses. As I mentioned at the beginning of the course, and as you all know, humans are very visual creatures. Most of our interactions with our machines are visual, right? Most of the time you're looking at a screen and tapping a screen. Can we broaden the senses that you bring to bear when you interact with the machine? How would we do that, and why would we bother doing so? That's what we're going to look at in lecture 15. Okay. So we're going to broaden human-computer interaction now. We spent some time talking about vision. We can also talk about sound. We're going to focus in the next few applications on touch, which is sort of the most underappreciated of all of our 5 or 6 senses, depending on how you count. We're going to distinguish at the outset here between touch and haptic perception. Whenever we're talking about vision or sound or touch, we can think about the raw sensation itself, which is a passive process, right? As long as your eyes are open, there are photons that are falling on your retina. You can't do much about that unless you close your eyes, right? But visual perception is an active process. Remember a couple weeks ago we were looking at all those optical illusions? Your brain takes that raw sensation, that raw visual sensation, and actively tries to add meaning to it and make sense of it, right? In the same way, you can think about touch. The minute your skin comes in contact with something, or you may actively cause it to happen, but you're registering raw sensation, raw haptic sensation, and your brain, like with visual input, is trying to extract meaning from it, right? So tactile devices, which we're going to look at in a moment, are relying on this haptic perception. How might a machine push that back against your skin and help you build up an understanding of what it's trying to tell you or enrich the interaction with the machine in an interesting way? We have, at the moment, lots of input devices that rely on touch, or at least muscle power, right? You tap your keys, you move your mouse, you touch your touch screen. But there are relatively few output devices that touch back, right? That actually give you tactile information. There's some interesting HCI research projects out there, like the MIT interactive pin system here. Has anybody seen this moving pin display before? It's not a display, I guess. Okay, let's talk for a moment. I'll show the rest of this video in a moment. What's happening here? Can I pause it and get rid of this? Yes. What is happening here? The pins are moving and following the shape of his hands. How? So we have, remember this cartoon, right? We have a human and a machine, which we have here. The human is doing something which becomes input to the machine. The machine outputs something which becomes input to the person. What is the input and output of the human in this case, and what is the input and output of the machine?
I actually think this is pretty similar to what we're doing with the motion device. Like, there's some way that it's I don't know if it's like a motion sensor or gloves, but somehow it's like detecting X, Y, and Z coordinates for his hands, and instead of like putting that to matplotlib, it's like using pins that simulate like those positions.
Absolutely, right? So not so far from the leap motion device. The output from the human is movement of the hands, which becomes input to the machine, which using some device is being translated into X, Y, and Z coordinates of the hand. That's the input to the machine. What is the output of the machine? What is it doing with that X, Y, Z? It's moving the pins, right? So it's looking at X, Y, Z and figuring out there's a whole bunch of actuators or motors under the table that are pulling and pushing these pins using that information. So that's the output of the machine. What is the input back to the human? What does the human feel or see as a result of this interaction? We've got one more step to close the loop.
Is it the visual height or movement of the pins?
They're looking through the laptop at the screen. So they cannot feel the ball, right? They feel their hands moving because they're actually moving their hands, and they see the ball moving, but they can't feel the surface of the ball on their palms, right? So there's no actual haptic feedback to the human. However, when this happens, it feels as if you're touching the ball, which is kind of strange, right? You're seeing it happen. Why is that the case? If you ever get an opportunity to try this, it's kind of interesting.
Is it because our visual and motor are so interconnected that your body assumes that if you're looking at yourself holding something, like your brain simulates that like you actually are holding something?
Absolutely, right? So remember that the brain is a prediction machine, right? So imagine you're using this device, you're moving your hands, and your brain is predicting you're going to feel certain strains on your muscles, which is the weight of your hands as you move them. That all makes sense. And the muscles in your arms tell you that your hands are in front of you and that your eyes are open. So your brain predicts you're going to see your hands, which you don't. What you see is something that looks pretty much like your hands, not quite. So that's supporting a big part of the prediction. Your eyes also tell your brain, all right, I see your hands more or less, and I also see that our hands are holding a ball. However, the touch information, the touch sense in your skin is not reporting the ball. Your brain says pretty much everything is there. 90% of the prediction is holding up. There's a missing 10%, and your brain fills in the rest. You remember our discussion about cognitive psychology? The brain does that all the time. If you write an essay and you read it just before submitting it, you don't see any spelling and grammatical errors. You submit it, the instructor marks it, it comes back covered in red ink. And you think to yourself, where were all these spelling and grammatical errors just before I submitted them, right? Your brain filled in for you. Word wasn't perfectly spelled, but your brain knew what you meant, and on it went. Same idea here. So they're using not a Leap Motion device, but a Kinect camera, so more or less the same thing, basically just cameras that are translating 3D. It works with not just hands, but other kinds of objects. I'm waiting for him to turn it on, right? What do the colors represent? Good question. So sometimes there's color and sometimes there isn't. Depends on the application. There's a tactile metaphor. I haven't seen one of those yet. What do the colors mean here? Move towards me, right? Put the ball on green. It's a game. Exactly, the arrow, right? Go forward, go back. So now there is actual tactile feedback, right? The interaction is a little bit different. Matplotlib in real life. Teaching math. What does the quadratic function feel like? Literally. There's the actual system. Okay, with most HCI applications, the other ones we're going to see today, it's look what we can do. What's the killer app here? Again, who knows? What might be the killer app here?
What about teaching blind people things?
So there's actually a group of faculty here who are developing moving pin displays for exactly that, right? So trying to translate anything you might be able to see on a computer screen into a moving pin display, right? So teaching the unsighted, serving an underserved community, especially as ubiquitous technology starts to take off. This is a big issue now in society as a whole, right? We want to make sure that people aren't left behind.
Larger scale, if you had a small apartment and you wanted to like raise your bed,
There you go.
Sleep.
Okay.
Well with bed.
All right.
Obey.
All right. Talk to me afterwards. We'll get this. We'll get the intellectual property lawyers on this one. That sounds like a good one. Okay. So there's an output device which literally pushes back. So as we move forward in this section, we're going to see more and more devices which look less and less like a traditional computer and are able to interact with us on our different sensor modalities. But they can also, the devices themselves, can push against the world and observe how the world pushes back. What other output devices could you imagine besides moving pin displays? What other existing output devices exist that give you information through the skin? That present information to touch rather than vision or sound?
I know a lot of smartphones nowadays, they use like vibrations to communicate different things.
Absolutely, right? So sometimes it's pretty simple, just a binary signal, right? You've got a text message. Pretty simple, but pretty effective. Yep. Most of the time you're visually or auditorially attending to something like this lecture. So the nice thing about vibration is it can sort of provide you information in the background. Remember when we talked about attention, it's this sort of idea like computation. You can allocate more or less attention to something. Hopefully you're allocating most of your attention to the lecture, but you might have a little bit that's waiting for a text message and registering that you got one, and then maybe you'll check it after class. Okay. Let's have a look at another one. This is the Ultra Haptics display. This one is kind of interesting, as you'll see in a moment. This one is also going to supply tactile information to the user, but is also not going to supply tactile information to the user. Okay, this one requires sound, so just bear with me here.
Interactive surfaces are now common in everyday life. Interactive surfaces are now common in everyday life. They allow users to walk up and use them with no instruction. However, current methods for providing tactile feedback require the user to cover up the visual content by touching the display or attach devices to their hands. We present Ultra Haptics, a system that provides mid-air haptic feedback and requires no contact with either tools, attachments, or the surface itself. Ultra Haptics uses a phased array of ultrasound transducers to create tactile focal points in mid-air. The array is driven by a stack of 5 driver boards, which receive emission patterns from a PC. The user's hands are tracked by a leap motion controller, and the haptic feedback is projected through an acoustically transparent display directly onto the user's bare hands. There are 4 steps to our unique focusing method. First, we define a large volume around the transducer array, within which we will model the ultrasound field. Then, we position positive control points where we want to form focal points. These tell the system to generate the highest intensity ultrasound possible at these locations. They are then surrounded with null control points. These have the opposite effect, telling the system to generate the lowest intensity ultrasound at these locations. Finally, the phase delay and amplitude are calculated for each transducer in the array to create an acoustic field that matches the control point. This simulation illustrates the acoustic field as we move up from the transducer array. Color represents phase, and brightness represents intensity. At a height of 20 centimeters, a focal point is formed. Above, the ultrasound defocuses once more. Similarly, this simulation shows 5 discrete focal points being formed at the same time. By varying the tactile properties of focal points, such as the frequency, they can be made to feel different from each other. In this scenario, a tactile information layer is created above the display. By moving their hand over the map, the user can feel the population density of a city. The frequency of a focal point represents the density in that area. Here, focal points are created above elements of a music player interface. This allows a user to locate themselves on the interface without looking. Tapping the focal point above the button starts and stops the music. The focal point above the volume slider can be grabbed. At this point, it pulses to inform the user that the system has recognized their grasp. The focal point can then be slid up and down to change the volume. These are just a few of the applications that become possible with the Ultra Haptics system.
Okay. What's happening here? They grab the volume knob in midair, and of course there is no volume knob there. But if you ask the user, it feels as if there's a small sphere floating in midair that they grasped. And when they grasped it, they felt it vibrate slightly, which was the volume knob in midair telling the user, I've got you, I know you're holding me, and I'm ready to slide back and forth. How is this possible?
So is the idea that if you focus ultrasound waves to one point at a certain height, that will actually feel like something is there?
Absolutely. So they're basically vibrating the air at a very high frequency, right? So your cell phone in your pocket is vibrating and you feel it. If there is a vibration in the air very close to your skin, you will feel it. It's ultrasound, it's very high frequency, so it doesn't actually feel like a vibration. The frequency is so high that it doesn't feel like something that's shaking anymore. Eventually it just feels like something that's solid. Okay, you mentioned they focus somehow the ultrasound. How does that work? Well, they mentioned they have a transducer here. So transduction means translating one physical phenomenon into another. So they're taking electrical signals from a PC, so just code is being sent to this transducer, which tells a 5x5 set of these transducers how much ultrasound to emit at what frequency and at what amplitude. So they mentioned this is a phased array, meaning that these 25 transducers are often emitting ultrasound with a bit of a phase offset. So it's not that they're sort of directing a beam of ultrasound, they're changing the phase offset. Why does that matter? Imagine you had an outdoor kiddie pool and a bunch of you stood around the edge and held edges of the kiddie pool and you could shake the edge of the pool up and down. If you all shook it in the same way, there'd be one big wave that would move from all of you towards the other side of the kiddie pool. But if you do this for a while, you can figure out how to shake the kiddie pool at different frequencies. So nearby, there's relatively calm water, but you cause a wave to appear at the far end of the pool. Because you're influencing positive and negative interference between waves of water, or in this case, sound waves of ultrasound. So you've all probably seen this at the beach where you have two waves that come together, and if they hit at just the right angle and just the right timing, there's positive interference, and there's a resulting wave that is twice the height of the original two waves, right? Same thing here. You have these emitters that are sending out signals at different phased array, and at different phases, as they move upward above the device, they collide in complex patterns and produce more or less ultrasound. In the same way, you've probably seen two waves that come in and they're offset by a little bit and they sort of cancel each other out. The height of the wave and the trough of the other wave meet and they cancel each other out. That's negative interference. So by setting the phase offsets carefully, you can create positive and negative interference at different points in three-dimensional space. The metaphor of the waves on the beach is still sort of in 2 dimensions, or 2.5 if you want. This is being done in 3 dimensions. So they mentioned putting these positive control points. So they're setting the phase offset of these transducers so that they meet and produce more vibration at those green crosses. But they're also setting the phase offset in such a way that just around the point, they're also canceling out some of the vibration. Otherwise, if they don't cancel it out and you put your hand in this device, you sort of feel this mild vibration everywhere, right? So they're sort of taking away vibration around the 3-dimensional point where they want you to feel a small object. Make sense? How do they know where you're grasping in 3-dimensional space? Good old leap motion, right? So the input to this device is the 3D coordinates of the bones in the hand. The user's hand is here. Depending on what the display or what information you're trying to give to the user, the output to this machine is frequency and phase offset of these 25 ultrasonic transducers. That's the output of the machine, which becomes input to the human, which in this case is tactile input. You feel that your hand is touching something. Okay, kind of interesting. Again, I'm not sure what the killer app is here, but a very interesting concept and a very exotic form of interaction. Galen.
You necessarily need the tactile input. Like, couldn't they do the same thing without all the whistles?
Absolutely, right? Why would you actually need to feel something in 3-dimensional space? I don't know, right? Are there applications you could think of where it might be more interesting to manipulate things in 3-dimensional space and feel that feedback compared to just seeing it on a screen and touching a 2-dimensional surface? Ideas? Where might that be useful?
Combining with holograms?
Possibly, all right, so maybe we project visually in 3D as well. So maybe you do see the object in 3-dimensional space and you feel that it's a solid object.
Once again, I think this is really useful for people who are visually impaired to help them like directly interact with stuff that they can't see.
Absolutely, right? So you're literally feeling it, right? We don't necessarily have to rely on the visual feedback. Where would it be useful to feel something rather than see it?
I know I saw a similar video talking about how in the automotive industry this could be potentially useful just because they're getting rid of buttons for like touchscreens now in a lot of cars, but you have to look at a touchscreen and know where it is instead of like a knob that you can kind of just feel out.
That's true, okay, possibly. So again, you can keep your eyes on the road. Maybe there's an application, some adaptation of this application where you're being provided with tactile information, but you're able to keep your eyes on the road. Imagine you're in a partially autonomous car and there's some vibration coming through the steering wheel, or maybe your hands aren't on the steering wheel, where the vibration or the form of the vibration is real-time feedback from the car about certainty. One of the most important things about an autonomous car might be to be able to tell you unobtrusively, I'm not quite sure what's going on. I'd prefer if you grabbed the wheel at this point and gave me a little bit of feedback. And it would be nice if it would be able to tell you that without grabbing your visual attention at exactly the point where the autonomous car is unsure about what's happening, right? It may be a very small period of time in which tactile information may be preferable to visual information, but it could make all the difference. Again, who knows what the killer app is, but thinking carefully about the person and the task, which is keep your eyes on the road as much as possible, things like this might be useful someday. Not yet, but someday. Okay, so again, why haptics over vision? Well, one of the nice things about manipulating a physical object, or a quote-unquote physical object, you may not literally feel a physical object, but it might seem that way to your brain, is that we often bring all of our sensor modalities to bear on the problem. So touch is one of the underappreciated sense organs that we have, because often when you grasp an object, you're also looking at it. You might see it deform, or you might see the result of your manipulation of that object. Maybe not in the ultra haptics display because there's an object that's invisible, but maybe with holograms or something else, we can sort of not just project to touch, but project to our visual, auditory, and tactile sense organs. What else is brought to bear when you grasp an object other than vision? You feel the object, obviously. You see yourself grasping the object. What else might happen as you physically manipulate an object? Some of you are writing with a pen right now. You're manipulating an object. What's happening? The information that's coming back is not just touch. Auditory. Maybe you hear the scratching of the pen, right? If you grasp an object and you stroke it across another object, you learn a lot about the material properties of both objects because you hear it, and you're generating it as you do so. Absolutely. So imagine you had access to the Ultra Haptics display and you wanted to teach somebody calligraphy, or you wanted to teach someone how to use a paintbrush or a pen, right? So now you're not manipulating a button, you're manipulating an oblong cylinder, and you need to infer somehow, is the tip of that object coming into contact with the surface, right? You know that with a pen because the pen pushes back. You can see that you're coming into contact with the object, but all those sort of subtle interactions are going on all the time. Remember when we talked about cognitive psychology and attention and prediction? Your brain is making obvious predictions like, I see the tip of the pen come into contact with the paper, but there are also more subtle things going on, like I expect the pen to push back when I touch pen to paper, right? You need to capture all those things in a haptic device as well. Okay, again, here's some of mine. You can obviously, through your own intuition, come up with a lot of these. You learn a lot about an object when you grasp it. There's a very good reason why young children will grab any object nearby. Their visual sense is usually not very good, at least in the first year of life. A lot of what they see is still kind of blurry. If your vision is blurry and you don't know much about the world, best thing is to try and grab brightly colored objects and put them in your mouth. Why put them in your mouth? Because your mouth is a great tactile sensor. If you want to learn about an object, put it in your mouth and bite on it, and you'll learn quite a bit about that object. Is it malleable? What's the temperature? Is someone going to yell if I bite on this object? They're learning the difference between self and inanimate objects and animate objects. That matters. How does an object move across other objects? What do we want to learn about interactions between objects by manipulating? How does it resist our grasping of it? Is it heavy? Is it soft? Is it light? Does it separate from the other objects that I see? Is it attached to those objects? Is it separable? It's often, if you don't know much about the world around you and you see objects, you don't necessarily know a lot about their properties. Vision is great because it gives you a lot of raw information. But unless you know a fair bit about the physics in the world, you can't really infer stuff about the physical properties about an object unless you manipulate it. Okay? If you want to play around with your leap motion device and try and teach people how to manipulate objects in three-dimensional space, if you've ever used a CAD program, for example, it can be very difficult as you're creating an object in 3D CAD to rotate it to a desired angle. You sort of have to click on something and drag along the x-axis and then click on the y-axis and drag along the y-axis. It's complicated, non-intuitive, takes a lot of practice to get good at it. Wouldn't it be great if you could just reach in, grab the object, and rotate it to the 3D orientation you want, right? It's very intuitive to us. Hopefully some of you are still more comfortable with sketching or writing with a pen than you are on tapping to a screen. Maybe that's not so true anymore, but for most of us, I think if you want to draw something, it's still useful to grab a pen or a brush or a stylus and make a mark on a surface. Right? So if we can, again, leverage all of those intuitions that we have, we might be able to build some interesting tangible and tactile devices. Okay, here's another one. I think in the interest of time, I'll just play the beginning of this video.
Illuminating Clay allows users to simultaneously interact with both physical and computational representations of the landscape. Here we see two collaborators preparing a landscape model to be analyzed with the system. A Vivid 900 Minolta laser scanner allows the topography of the model to be captured at a rate of 1 Hz. A Mitsubishi LCD projector casts the results of the landscape analysis back onto the surfaces of the model. The work table comprises of a smooth white surface and a rotating platform onto which a landscape model is placed. We experimented with different types of landscape modeling materials. Plasticine with a ductile fibrous core allows the model to maintain the required topography. The area around the platform is illuminated with a library of analysis functions that can be selected at will. The remaining edges of the work surface are used to project cross-sections.
Okay, what's the interaction loop here? There's obviously an important tactile component here. The users feel the manipulation of the clay as they're manipulating it. What is the input and output to the collaborating machine in this case? So in the previous example, we had leap motion, which was capturing the 3D position of the hands. In this case, there's no leap motion device. What is the input to the computer in this case?
The height or peaks and valleys of whatever that model structure is.
Exactly, right? So now we have a third object, a physical object, which is providing the input to the machine. And the input that's going to the machine is indirectly being dictated by the human who manipulates the topography of the clay. Right? The output of the device is visual in this case. It's projecting some visualization back onto the surface. What's the killer app here, if there is one?
Seems like maybe for like GIS data analysis could be really useful.
Okay.
You can, like 3D print the landscape and then you can project like tactile information onto it.
Okay, so GIS information system, geographical information systems. So we might want to rapidly try and model a particular landscape. You could use this for urban planning. What happens if we put a park here? What happens if we manipulate the landscape in this way? And as you're thinking that through, you're physically creating the model, and in real time, the system is telling you the repercussions of those actions. So the moment that you create hills in this landscape, if you watch the rest of this video, you see that it will fill blue into the valleys, right? So obviously the water is going to pool in the valley. So you can immediately see what that would look like. Again, you could do it with CAD modeling software, but it's much less intuitive, right? It would be great to manipulate something and see our ideas literally taking shape. And in addition, which you can do just by playing with clay, right? But in addition, with HCI, you can see in real time the repercussions of that. Remember, the brain is a prediction machine. If I do this, what will happen? If I do that, what will happen? Right? Here's a way to help support that cognitive process for GIS or urban planning or architecture, and away you go. Okay. The last one we're going to look at, the last example we're going to look at here is the actuated workbench. In this case, the device itself is going to move an object. So now we're getting more and more into devices which are pushing against the world and observing how the world pushes back in interesting ways. The first example we saw this morning, there was also an object that was being moved around, which was that red ball. But ultimately, it was the human that was doing the moving. They were doing it very indirectly, right? But here, the machine itself is going to move objects in the world.
The actuated workbench consists of an 8x8 array of electromagnets. It uses magnetic attraction and repulsion to move magnetic objects two-dimensionally on a flat surface. Here we can see a magnet moving in stepwise Manhattan motion. Here we see an object moving in a smooth circular pattern. Although the array of electromagnets is fixed, the system can create smooth motion by varying the strength of the electromagnetic fields. In addition to magnets, the electromagnetic array can move any small ferromagnetic object, such as a paperclip. Here the user controls the puck's motion with a trackball. Smaller objects can be moved much faster, though their motion is not always so smooth. Magnets of different sizes and shapes behave differently in the system's magnetic fields. This stack of small magnets jumps around whimsically. We use computer vision as a preliminary object tracking technology. Here the user records a path by moving the puck on the surface, and the system then replays that path through magnetic actuation. The blue projection around the puck is a graphical visualization of the strength of each adjacent magnetic field. Here is an example application intended to teach users about physics. The red projected area on the surface represents a zone of attractive force, while the blue area represents repulsive force. The user can feel these forces by lightly holding the puck in different areas of the board. When the user releases the puck, it flies to the red zone of the board, to which it is attracted. Magnetic drawing toys are effective for visualizing the actuated workbench's magnetic fields. A magnadoodle allows us to see the fields used to trace the smooth circular path shown at the beginning of this video. The Dapper Dan toy lets us see the magnetic activity in the movements of iron filings on the surface. The actuated workbench can be used to control the planchette in a Ouija board game.
Right? That's it.
Like other robust systems, such as the Diamond Touch, presented by Mitsubishi Electric Research Labs in WIS 2001, the actuated workbench works even when set on fire.
Very important, right? Whatever the killer app is, I'm not sure here, but apparently it's going to be used in a very flammable environment. Interesting. Okay, so again, who knows what the killer app would be here? The actuated workbench shares something in common with the Ultra Haptics device, which is we have, I don't know if it's 5x5 here, but we have an array of transducers again. So transduction takes one physical phenomenon and translates it into another. In this case, we have electromagnetic transducers, which take as input electricity or commands from the computer and translate them into local magnetic fields. In the Ultra Haptics device, you're taking electricity or commands from the computer and turning them into pressure waves, ultrasound. Okay, so now we have a device that's actually moving an object. Remember that we now have a computer that's interacting with a person, and often we're trying to, in HCI, draw on people's intuitions about a person interacting with the inanimate world, or somebody interacting with someone else, right? A social process. So an important part of social interaction is teaching, right? If you've ever, when we were young and you learned how to write, the teacher would demonstrate it, and you would visually see the teacher writing something from a distance, but you couldn't feel what the teacher felt as she was writing on the board for you. You had to infer from your visual system what she was feeling, translate that into actions, and predict in your brain whether your felt experiences of the act of writing match whatever she felt when she was writing. Right? That's a pretty big cognitive leap, which makes things difficult to learn how to write, to learn a musical instrument, to learn a sport. You're learning something that is very motoric, has to do with our motors or our muscle system. The best way to learn would be to actually feel what it feels like to perform that action by the demonstrator, the instructor. Probably would learn that much faster. That's what the actuated workbench helps with. How does it support that particular interaction? There's still only one person here, at least one person at a time, using the workbench.
But what if we imagined kind of an app that teaches you how to write, and so you have a magnet that moves around and traces the letters, and you can hold on to the magnet?
Exactly. So partway through this video, you saw this imitation, right? Somebody did something, performed an action, they moved the device. The computer was clearly sensing that movement. The computer then reverse engineered from the movement of that object, had to reverse engineer what are the magnetic fields, or how should the magnetic fields change over time to reproduce the same actions. So there's some machine learning there, right? Once it figures out how to do that, the machine can play back an action performed by a demonstrator. And if you hold that device as the student, if you hold it lightly, the object will pull your hand through that action, and you will feel more or less what the instructor felt when she performed that action. Right? That is an interaction that was impossible before something like this device existed. Right? So one of the things that we're trying to do in HCI is create technology that supports social interaction, which in this case is someone teaching someone how to do something else. Trying to support a social interaction that was difficult or impossible to do before. Right? The impossibility here is it's impossible to literally feel what somebody else feels when they're performing an action. Right? This might make it possible. And it resists being set on fire. Very important. Okay, we got a few minutes left, so let's switch now to lecture 16 and ubiquitous computing. This is a little cartoon I showed at the beginning of the course. Back in the Stone Age, we had just humans, and only a few of those humans had computers, and a very few had cell phones. Today, most people in the world have one or both of these, and there are many more cell phones now in the world than there are computers. An interesting demonstration of HCI. There's something about holding a small computer in your hand that is preferable for some people over others, for cultural, financial, physical reasons. We're now starting to see the deployment of embedded devices. So these are devices which themselves are stationary, but talk to other devices that are in their range of view. So Wi-Fi tower. So we have an embedded device now which itself can't move, but it can communicate with other objects. And we're going to end this session on looking outward by looking at another class of HCI devices, otherwise known as robots, which can move themselves. So the actuated workbench that we just looked at is almost a robot. It can move things in the physical world, but it cannot move itself. The actuated workbench can move an object and sense the repercussions of the movement of that object. A robot can move itself and feel the repercussions of that action. We'll get to robots in a few weeks' time. Okay, so how do we go about doing this? Well, ubiquitous computing as an idea has been around for quite a while. The term itself was coined back in the 1980s, and there's sort of two founding people in the field of ubiquitous computing, Ken Sakamura and Mark Weiser here in the US. Most people who work in computer science eventually hear about Mark, who actually coined the title ubiquitous computing. He came up with this at the then famous Xerox Palo Alto Research Center, or PARC. A lot of innovations in HCI and computer science came out of PARC. Ken Sakamura, at least in the US, is not known as well, but he has been immensely more successful in the sense that he realized way back in the 1980s, as personal computers were just being invented, that even if personal computers happened to be successful and a lot of people bought a personal computer, they probably wouldn't buy 2, and they definitely probably wouldn't buy 5. However, after the PC revolution, there might be other devices other than PCs that have specialized uses, and there's no limit in how many of those specialized devices people might have. This is back in the 1980s. This was pretty prescient at the time. Think about all the devices you own, right? It's probably more than just your laptop these days. If you own a car, there's another one, right? There's a lot of electronics. There's a lot of HCI in cars these days. So the number of devices that we have is much larger than your laptop. So around that time, Ken started to develop Tron, the other Tron. the real-time operating system nucleus, and this was an operating system that was developed specifically for devices, specialized devices, and it's a real-time operating system. So in a way, your Leap motion device, or the Leap Python package, is close to this idea in real time, that you can grab a frame of data at any time from the device. If you don't grab a frame of data from the device and someone waves their hand over it, that data is gone. You missed it. Right? That's very different from sort of traditional programming, where assuming there's an external database, the data is kind of static. You can go and collect that data at your leisure. Time is not an issue. Right? In real-time devices, time matters. Right? There is continuous information that is arriving at the sensors of the device, and you either grab it or you don't. It very much changes your way of thinking about coding, and you probably got a taste for that in the first few deliverables of this course. Tron, again, this is a dated slide. I think this slide's about 5 years old. So 5 years ago, Tron was being shipped in 2 to 3 billion devices annually at that time, and at that time, there were about 200 million Windows machines being shipped. So 2 orders of magnitude more instances of the Tron operating system compared to the Windows operating system. How many people have heard of the Windows operating system? How many people have heard of the Tron operating system? Interesting, right? So if anybody asks you what's the most popular operating system out there, now you know the answer. Okay, so ubiquitous computing, this matters because it scales, right? And it's scaling faster than laptop and desktop and even phone apps and technology. As we start to deploy more and more devices, we realize that there are niches for more and more specialized devices. There's a bit of a feedback loop going on there. How do we go about deploying these devices out there? What's the right way to do it? Remember our discussion about design philosophy. There's different ways we could stitch computation into the physical world. Some may be better than others. In Mark's original paper on this, he said our computers or our embedded devices or the devices we deploy should be like our childhood, an invisible foundation, right? I can't see your cell phones, but I know they're here. They're in the background, they're helping you, but they're not monopolizing your attention at the moment. An invisible foundation that's quickly forgotten. You might forget that the vibration mode is set on your phone until it vibrates. But it's always with us and effortlessly used throughout our lives, like our childhood. Somewhat tongue-in-cheek in this paper, he referenced Philip K. Dick's novel called Ubiq, which sort of looks at the dark side of ubiquitous technology. What else has Philip K. Dick written that you might know of? Do Androids Dream of Electric Sheep, which got turned into the Blade Runner movies. The Man in the High Castle, I think, is currently on television. If you don't know about Philip K. Dick and you're a computer science student, you should. There you go. All right. Okay, so how do we go about doing this? There was a mention of childhood already. So we're going to touch on this last slide for today on another aspect of psychology. We talked about cognitive psychology, the way in which the adult brain works. What about developmental psychology? How do infants learn about the world and become functional adults? Children rely on the ability of their parents to scaffold their experiences. So as we start to put ubiquitous technology out there in the world, what is it doing for us? Hopefully, it's scaffolding our experience. It's teaching us things, it's helping us do things, but it's doing it in a gradual manner. So there's a picture on the right. Most parents end up teaching their children to walk in a way somewhat like this. You very rarely see a parent say, all right, kids, stay over there. This is what walking looks like. Do it, right? Because again, that doesn't work very well. First of all, kids don't have very good visual systems. So by scaffolding the child, and better yet, lifting the child and putting the child's feet on the parent's feet, the child can feel what the parent feels when the parent is walking, right? This is a tangible, interactive loop here. The important part about scaffolding, as the name implies, is as the learner starts to grasp the rudiments of the task, you very gradually start to release the scaffolding. I can't remember if it's deliverable 9 or deliverable 10, but that's exactly what you're going to be doing in that deliverable. You're going to start by making it very easy for the user to know what to do, what to sign. And whatever visual or auditory metaphors you provide to get them to sign correctly, you're going to gradually start to remove that scaffolding as the user gets better and better at the task, until eventually you should be able to flash up the digit 3 and your user does this nicely centered over the device. Okay, I think we'll leave things there. You have a quiz due tonight, and you have deliverable 8 to get started on. See you next week.
Sure.